Hey guys, let's discuss new topic from system design, which is called database scaling. So till now we have scaled our application using the load balancer or caching, but here let's say your DB is very slow, then you need to scale DB as well. Okay, so let's see, you have one application means this is the user, and these are services. This is load balancer. Okay, and then somewhere here you have a cache, and then here you have a database, but this is a single database server. So now single database server, so what are the problems with this single database server? See, the first one is let's say you are getting millions of user accessing your application, millions of requests you are getting per second. Okay, and then so it means that you have a high read and write traffic. So in that case, what are the issues here? See, the first issue is regarding the CPU. Okay, so you will have, first is CPU bottleneck. So what is CPU bottleneck? You're getting millions of requests, okay, and your CPU is limited. So in that case, it will create one problem. Second is you have a input output, limited input output. Okay, disk input output limits. So now the third one is a single point of failure. Okay, so if this DB goes down, entire application will crash. So to overcome these problems, we will use scaling. And now you have two types of scaling. Okay, the first one is vertical scaling, and second one is your horizontal scaling. Okay, so horizontal scaling. So vertical scaling, you call it as scale up, and horizontal scaling, you call it as scale out. Okay, one is up, second is out. So what is vertical scaling? So in vertical scaling, you just increase the so you increase the RAM or CPU of a system. Okay, so you increase the resources. So CPU you increase, then you increase RAM as well. Okay, and so here what is the pros? This is very simple. You just increase the capacity of that particular machine. Okay, this is the pros. But what is the cons here? Cons are that you have a limited scaling. See, there is one limit that you can scale this system. Okay, how much CPU you will increase, how much RAM you will increase, there will be always be one limit. So it means that you have a limited scaling. Okay, the second is this is expensive as well, right? And then you don't have any fault tolerance here. So for example, if your if any problem comes here in this DB, you don't have the replica of that, right? So you need to create replica also of that, and that too again will be very expensive because already this DB size is very much. Okay, and then you will create a replica of that. So that is the problem with vertical scaling. Okay, now what is horizontal scaling? So you call it as scale out as well. So here you will have a multiple DBs, okay, like DB1, DB2 and DB3, and that too in all different servers. Okay, so now you have divided your DBs into multiple DBs. So in that case, this is scalable. Okay, so you can add multiple DBs. Yeah, how many DBs? You can add any number of DBs. Okay, it is not limited that you can use this much only RAM or CPU. And then the second thing is this is fault tolerant also, right? So if this DB goes down, your entire application will not crash. You still have other DBs also. Okay, so now there is a concept of one more concept which is called replication. Okay, replication. Now what is replication? Replication is nothing but just the create a copy of a data, okay, in a multiple server. So as I was talking about that this is not fault tolerant. Okay, the system is not fault tolerant. So replication, you can call it as read scaling as well. Okay, so here what you do, you create a, let's say you have a 1 DB. Okay, you will create it's a copy, multiple copies. Okay, according to your requirement you create multiple copies, but here there will be only one master and other will be slave. Okay, slaves or followers, you can say. So one master in the sense that whenever you need to do write operation, you will do that with this master node only. Okay, and if there are read operations, then you can read it from multiple DBs. So in that case, this is called read scaling because your read will be faster here, right? And Write will be slower because first you will write in one database, and then it will replicate into the other, it will sync from in the other DB, okay, this the new content. So this is the replication or read scaling, you can call it, okay. And so let's say if you have a query like select star from user, so this is your read query, okay. You are not doing any data changes here, you are reading from data, so that you can do with this slave nodes. And let's say you have a query like insert into user, this kind of query, so you will perform that into the master node, okay. Now let me clear this. So this was about read scaling. So we have seen vertical scaling, horizontal scaling, read scaling. Read scaling is nothing but your replication, okay. And then you have a different type of replications, okay. So type of replication, so first is synchronized, okay, and then second is non-synchronized. So what is synchronized, what is non-synchronized? See, in synchronized it will wait, so you have written in the master, okay, you have a slave nodes as well. So in synchronized it will sync, okay, serially. So means you will write node, you will write data in master, then after that master will sync that data into different slave nodes, okay, because all nodes should have the same data, right? That is called the consistency. So so in synchronized replication, master will wait, okay, for all the replicas. So once all the replicas will acknowledge the master that okay, we have written the data, then only master will acknowledge that okay, data write is completed, okay, data write operation is completed. But what is the problem here? The problem is this is slow, okay. This will provide you strong consistency, okay. We have already talked about a strong consistency and eventual consistency. A strong consistency means if you make changes in one database, okay, and you have a multiple databases, and if you query other databases, you will get the same result, okay, updated result. So that is called the strong consistency. And what is your eventual consistency? Means right now you will get a stale data, but after some point of time it will update other replicas also, and then eventually the system will be consistent, okay, but it will take some time to update those system. So this is called non-synchronized or async, you can say async replication, okay. So here so async though we have not talked about. So yeah, so this is called synchronized. And now in async, so as name implies that you will have an eventual consistency here, and then you will write in a master, okay, and then master acknowledge that okay, my write is done, and whenever master will get time, it will update sleeves, okay. So here you will get the eventual consistency. So this is the problem with this. So but this is fast, right? Because master has done his work, and then it will reply that okay, write is done. So this is fast. But in synchronized, master has to wait for a slave to complete their task, and then only it will say that okay. So this is eventual strong consistency but slow. Now so when so in async replication, you will have a problem, one problem, which is called replication lag, okay. What is replication lag? See, master has done his work, okay, and but at that time if you go to slave and will check that data, that data might not be present there, because right now slave has not completed his task, okay. So this so you will get this stale data. So this is called replication lag. Means currently it is not fully replicated to other nodes as well, okay. New data is not fully replicated in the other nodes, so there will be some lag. So yeah, now what will happen if this master will fail? See, you have only one node, master node, and you're doing write operation with that node, okay. So if this master will get fail, what will happen? So nothing, anyone from the slave, okay, nodes will become a master. So they will do a election, and then they will choose one master, and that master will become the main node. Write operation will perform with that master node. So now Okay, so one of the slave will promote it as master, and but yeah, during this time, let's say you are writing in the master and then master goes down. Now that data currently is not present in the slave, right? During the process only master goes down. So in that case, there might be some data loss happen here. Okay, so that is the drawback. And now the question arises how you can reduce this replication lag. Okay, so there is a problem with replication lag with this async replication. So how you can reduce that? So let me remove this first. Okay, so there are different ways you can reduce the lag. Okay, the first one is faster network. Okay, so the network should be faster. You're querying the data, right? For the data, so the network you're using should be fast, means data transfer speed between nodes should be fast. Let's say this is your master node, okay, and you have written in this master node, and now you have multiple slave nodes. So master will write into the slave node. So if your network is faster, okay, then you can decrease the replication lag. Okay, you cannot completely remove that, but you can reduce it. Then the second one is if you have a better bandwidth. Okay, so let's say you are transferring data here. If you have better bandwidth, then also the replication lag we can reduce. The third one is optimized protocol. So the protocol you're using for the data transfer should be optimized one. Okay, so these three things, like low latency network. Okay, the first one is low latency network, second one is optimized protocol, and third one is better bandwidth. Okay, so using these three ways you can reduce the database lag. One more thing you can do, fewer node. So let's say you have hundreds of nodes, so it will take much time because you need to do more work, right? So less work, so less timing. So just reduce the replicas. Okay, now we have another concept which is called sharding, and sharding is also called right scaling. So we have seen vertical scaling, we have seen horizontal scaling, okay, and then we have seen read scaling, so which is replication, and now right scaling. So right scaling is nothing but sharding. Okay, so now let's talk about what is sharding. Sharding is nothing but just divide your data into multiple servers. Okay, let me remove this. Okay, so so this is, as I told you, this is also called right scaling. And so in sharding you split large database into smaller pieces. Okay, and then you are distributing write load there. Okay, so you are distributing your write load now into multiple instances. So here let's say you have millions of user. Okay, and I'm saying that from user 1 to 1000 I'm storing in db1. Okay, which is on one server. From user 1000 to 2000 I'm storing in db2. Okay, so I can parallelly I can query them as well, so it will take less time. Okay, so this is called the sharding. This concept is called the sharding. What is sharding? Split large database into smaller pieces. Now there are different types of sharding. Okay, types of sharding. The first one is range based. Okay, so what we just saw. So in range based there will be a range, like 1 to 1000 should go to db1, 1000 to 2000 should go on db2. Okay, you have decided one column, and based on that column value you will divide the data. And so here I have choose user ID. Okay, let's say, so user ID is my you can say shard key. On the basis of user ID, on the basis of this shard key, I am splitting my data. Okay, now the next one is hash based. So what is hash based sharding? So in hash based you will find the hash of a user ID, let's say. Okay, hash of a user ID mod n is the number of server. So whatever will be the answer, we have seen this in consistent hashing. Okay, so there our distribution will be consistent to each server. So that is the different another way. Okay, so the second one was you can say hash based. Okay, the first one was range based. types of the sharding, and second one is hash based, and then the third one is directory based. So in directory based, actually it maintains one directory or a folder, okay, and where it will check that I want this particular data, which shard is containing this information. So for example, I wanted the user ID 2500, and which is there on DB3, okay, shard 3. So I will maintain one directory which is saying me that from 1 to 1000 it is in DB1, and 1000 to 2000 it is in DB2, and 2500 you will get in DB3. So that is called the directory based sharding. Okay, now as I told you about the shard key, so you're dividing data on the basis of one factor, and that factor is called shard key. Okay, so let's take some example of a shard key. Okay, this is very important to select shard key intelligently. Why? See, let's say you have a status field, okay, in database, which is called for your order status, let's say pending, complete, okay, and then in progress. So there could be the scenario when user is hitting and just wanted to know who all are the in progress orders. Okay, so you have one database where you are storing you have, let's say, 3 databases, and on the basis of this status you're storing value in these databases. Means all pending order detail will go to this database, all complete order detail will go to this database, and all the in progress data will go to orders will go to this database. Okay, so let's say there is a requirement that you need to find all the in progress, and there is a lots of query you are running in this database. So there is no use of doing sharding, right? Because these two DBs are not getting load, that much load, only this one is getting load. Okay, so no use of this, right? So while selecting a shard key, you need to keep in mind that the cardinality should be high. Okay, now cardinality should be high. Now what is cardinality? It is the number of uniqueness. Okay, number of uniqueness means currently you have only 3 orders: pending, complete, and in progress. Okay, these orders are containing a lot of data, so this should not be the sharding key. Okay, now let's take another example of bad sharding key. So this one was bad sharding key. Another one is let's say country based data you have stored. Okay, so I have created one database for US datas, and then second one is for India, third one is for Singapore. Okay, but now let's say you have a few dominant user from USA, okay, which is requesting this data. So again, the data distribution is means data load request distribution is uneven here, right? Everybody is querying this database. So again, this is the bad sharding key. So if I talk about the good sharding key example, the good sharding key can be your hashed user ID. Okay, hashed user ID. First of all, your user ID itself is a unique. Okay, and then you're finding the hash of that, and then using the hash of user ID mod n is the number of server, and then you will always get the new value. Okay, means different value. So the data request will be evenly distributed across the network. So this is the concept of consistent hashing. I have already created one video, please go and look that. And then second one is, let's say, email ID. I have sharded on the basis of email ID or username. Okay, so you have a unique email IDs as well. So this is the concept of good sharding key. Now there is one more concept which is called query pattern alignment. Okay, so now what is query pattern alignment? Let's say you have divided your data into multiple shards using one factor. Let's say the factor is, let's say, user ID, but you're querying, okay, you have multiple DB, and on the basis of user ID, okay, user ID, you have so user ID is your shard key. Okay, and you have divided data, and now you're querying your DB on the basis of email ID. Okay, email ID. So there is no logic, right? Means you have divided data on the basis of user ID and you're querying it through email ID. So you have to search in each database. Okay, you have to scan complete data. So this is also called query pattern. This is called query pattern alignment. Okay, this thing is called. So we need to keep in mind while selecting the sharding key, it should not be the bad sharding key, it should be come under the good sharding key practices. And then also we need to keep in mind this query pattern alignment thing. Okay, now the next concept is your cap theorem. So cap theorem is very important in system design. Okay, so cap stands for let me remove everything. Okay, so cap stands for consistency, availability, and partitioning. Okay, so CAP, cap. So cap is your consistency, availability, okay, and then partition tolerance. Now what is consistency? See, consistency is you should get the same data everywhere. Okay, consistency is same data everywhere. You have a 5 nodes in a system network, so in all 5 nodes the data you should get the same data should be consistent. So for example, you're doing write query, okay, in one node and in master node, and then slave is waiting for them, so it is not consistent, right? If you query to the master node, or you are querying to the slave node, you should get the same data. So like consistency lag should not be there. Then availability. So availability is your system should always respond, right? It should not be down, or user should not have to wait for the result. It should always be responded. So that is called availability. And then partition tolerance means handle network failure. So what is network failure? Let's say this is your node 1, this is your node 2, okay, and this is your node 3, and all 3 are connected in a network. Okay, this is your network. And now if these all 3 are connected, now let's say this circuit breaks, okay, or this circuit breaks. So now N3 is not connected with other nodes in this network. Okay, something happened. So means you have created one partition here, right, in the network. So this kind of partition tolerance will come under this P stands for partition tolerance. So it means that it should handle network failure. So how he will handle it? See, you will have a multiple copy of this N3. So once it will find that this N3 is not responding, so he will redirect all the requests to this copy of the N3. So this is called the partition tolerance. Now at a time you can always have a 2 out of this 3, right? So CAP. So here you can have a 2. And one more thing, in a network when you have a multiple nodes, okay, multiple servers, so you cannot ignore this P. It means that P should always be there, and I'm telling you that only 2 you can choose. So either you can have a combination of CP or AP, because P should always be there, so then you can have a C and P. Now what is CP and what is AP? See, CP is like consistency and partition tolerance, okay, and AP is availability and partition tolerance. So like for example in banking system, okay, what do you need there, consistency or availability? I need consistency there, because if user is doing some transaction, that transaction should be reflected same, okay, from each server. So availability, if the server is down, I'm okay, I'll do my transaction little bit later, but I want a correct data. Okay, so that is called the CP. So in banking system we use CP. And AP is availability, okay, and partition tolerance. So availability, let's say you have an Instagram or you have a Facebook, okay, and let's say the system goes down, so it will show you stale data in your feed. Okay, your feed is not up to date, but that is fine. Means I should not wait there. User should not get error or wait there for to get the new data. Okay, so that is available, but it is not consistent. You are still seeing the stale data for some time, and then the data will be updated. So in Instagram or Facebook social media app, you can use the AP. Okay, now another question is, can we have CA? CA means you don't have partition here. As I told you, partition will be same, should be there, okay, but let's say if you don't have partition and you have only C and A, consistency and availability, we can have this. But we can have this with the system which has only one node, because partition tolerance is related to the network, distributed network. Okay, so if you don't have partition tolerance should always be there. So then if you have a system of one node only, there is no network, so no need for the partition tolerance. Okay, so you can have CA there. Now let's talk about eventual consistency. Okay, so eventual consistency is data become consistent over a period of time. That is called the eventual consistency. Now let's talk about some advanced topic. Okay, advanced topic in this DB related advanced topic. So let me remove this everything, and now the first one is quorum. Okay, first one is quorum. So what is quorum? So quorum condition is read plus write should be greater than n, where n is the number of replica, okay, of particular data, let's say, or particular server. Write is your number of replica that must acknowledge the write operation. Okay, this is for the write operation. And R is number of replica that must respond to the read operation. So it means that, let's say you have one database and you have created it's a 3 replicas. Okay, so 1, 2 and 3, so this one itself. Okay, so 1, 2, 3. Now here I'm saying that I will have one write replica here, where if I need to perform write operation, so that will, or you can say that 2 write. Okay, so that should perform in this 2 database first, and after that eventually it will get performed in the other databases. Similarly for read, okay, so write is 2 here. Similarly for read, I'm saying that this one I'm using for the write, so these 2 I will use, second and third I will use. So let's say read first and second you're using for the write operation, and second and third you're using for the read operation. Okay, so you can perform read and write both in one database itself. That is what we do, okay, generally. So I'm saying that read should be performed using second and third DB. So now here if you see, the number of replica is 3, okay, and number of write operation, number of replica which will acknowledge for the write operation is 2, number of replica which will acknowledge for the read operation is 2. So here 4 is greater than 3. Okay, so this condition is true, so this is called the quorum. And in quorum, now here you have different, so why we are doing this, see, for the strong consistency actually. See, so when you are doing write, okay, so you will do write into this, let's say you have done some write here in this two databases. So this write will be do operation in this 2 databases. Okay, now you are reading the data, so that data will be, you will read with using these 2 operation. Okay, let me take different color here. So using this 2 you will do the write. Okay, using this 2 you will do the write, and using this 2 you will do the read. Okay, so here you have this node which is overlapping, okay, which is common, and using this node only you are finding that your data is up to date or not, consistent or not, or it will, if it is not consistent, that it will detect the stale data. So that is why we are having few nodes which are common in both, so that you can ensure the consistency. Okay, then the second one is leader election. Okay, concept. So in leader election, this is I have already told you, right? So in leader election, if master goes down, so process of selecting new leader is called the leader selection process. And what all tools you will use here? Tools you will use for leader election is Zookeeper, okay, then etcd, which we use in Kubernetes, and then Apache Kafka. Okay, and we will discuss this in detail after this, in this video only, later. Now, what are the common algorithm? Raft is the algorithm which we use for the leader election. Okay, that is also we will discuss in the theory part. Now let's talk about, so here we are talking about database, and that too the database are distributed. Okay, so in this distributed system, let's talk about then distributed transactions. So distributed transactions means you are querying in multiple databases. Okay, in multiple data, you have multiple databases and you're querying, your result is coming from the aggregation of result from different DBs. So that is the distributed transaction. You have two methods there. First is 2PC, okay, two-phase commit, and the second is saga pattern. Okay, so now let's discuss what is 2PC and what is saga. So in 2PC you will have one coordinator. Okay, so this coordinator will prepare a phase. This is the first phase, okay, phase 1. So here this one is strong consistent, and why it is a strong consistency? 2PC is a strong consistent, saga is eventual consistent. Okay, why? So in phase 1 what will happen? So coordinator will ask all the services that can you commit. Okay, so you have one coordinator, and let's say you have a multiple services. Okay, so first the coordinator will ask question to services that can you commit. So all the services will respond to this coordinator that yes. So this one is saying yes. So once coordinator will get all yes, okay, all yes. So so means services, what it will do? First it will lock the resources, okay, with itself. Means this service will lock resource whatever he has, then this service and this service, and then they will respond yes to coordinator. And then what coordinator will do? If all yes he got, then he will say that okay, commit. So all services will commit the data. If any one of the service will say no, okay, so he will roll back data operation from all the services. Okay, so that is the concept of 2PC. So this is strongly consistent, because either it will commit the data, okay, entire data will get committed in all the services, or it will get rolled back. So you will have a strong consistency there. So of course it is slow. Second is saga design pattern. So now in saga eventual consistency comes. Okay, so here you just break transaction into small transactions, okay, and then these small transactions you perform independently, okay, and then and it will have a compensating action, or you can say undo. If any transaction gets failed, so it will undo everything. So this is called the saga design pattern. Now in saga you have two types of saga pattern. So here first one is choreographer. Okay, so here choreography is basically event based. Okay, so event based, and second one is orchestrator. Okay, orchestrating, or you can say. So this is the central controlled. Okay, now what is choreographer and what is orchestrator? So in choreographer services will communicate each other using the event, okay, and then there is no central coordinator. So this is called the choreographer. And then for example Apache Kafka is the example of this kind of pattern. And then the second one is choreography. So in choreography you have a central controller, and then one service control the flow, okay, other will listen to that service, and then that service will call other services, and then they will do their operation. So now we have already talked about the consistency methods. Okay, so you have a 3 consistency methods, which is called, let's say, consistency method. Okay, the first one is strong consistent, second one is eventual consistency. Okay, these two we have already discussed. The third one is read after write. Okay, read after write, or you can say RYW consistency. So read after write is basically you have write in a database, okay, at least that database itself is consistent. Okay, maybe other will wait, but at least that database is consistent. So for example, I have uploaded one profile photo, and then I will check my profile, so I should get that updated profile photo on my profile. Okay, maybe other will get notified later, or it will get updated later for them. So this is called read after write. Okay, now another thing is multi-region database. So multi-region DB. So as name suggests that you are putting DBs in different regions, availability zone in the AWS. Okay, so one region is here, second region is here, so you will keep your database in multiple regions. Okay, so this is called the multi-region database. And so if I talk about the advantage, so this is low latency. Okay, why low latency? Let's say my equivalent datas are in same region only. Okay, I should divide my data such a way that related data should be in one region. And then the second thing is user is querying from this region, so he should get data from this region itself. Okay, if Indian region, okay, if some person from India is querying data, so he should get from Indian region, or from USA he should get from there only. Okay, so low latency is there. Now what is the another thing? High availability. Okay, this one will be available as well. You can replicate database also in that region. And the third one is disaster recovery. So disaster recovery, let's say some war or something will happen, and they will destroy the data centers. Okay, so you can have the data center in another region also, so you can use from there, you can redirect your request to those data centers. So that is the multi-region database. Now the same thing you can apply for geo replication as well. Okay, so now what is geo replication? As I told you, if war happens, okay, and some country destroy the data center, then the query will the request will redirect to another region's data center which has the same data. Okay, with this one, so that is called the geo replication. You are doing replica of a data on basis of the geolocations. Now in geo replication you have two types. Okay, the first one is active and second one is active passive. Okay, so in active passive, let's say I have a region 1, I have a region 2. Okay, and I have my DB here, same database. Okay, same data I have in this DB. So now here and then one more, region 3. Okay, here also I have the same data. Now when I'm doing write operation, performing write operation, so this one is master, and all the write should be performed here, and then it will later replicate that new changes to this R2 and R3 region database. Okay, so this is called active passive. So this one is active and these two are passive databases. Okay, now you can have multiple active users also, multiple leader as well. So let's say this R1 and R2 is a active. Okay, so whenever I perform write operation, it will go and perform here also and here also in two databases, and later it will replicate in another passive databases. So this is called active. Okay, so now multi-leader. In active you will have a multi-leader, and here you will have a one region active for the write operation. Okay, now the another thing, the last thing what we will discuss is the latency versus consistency trade-off. Okay, so this is very important. See, think about it, latency versus consistency. If you wanted to design a system, okay, so what you will prefer? Will you prefer latency or will you prefer consistency? Because at a time one only will come, correct? So I will think that which application I'm creating. So as I will give the same example again, if I'm creating banking application, okay, so I will be preferring consistency. Okay, if I'm creating a social networking site, then I will be preferring latency. I can show the same data to user for some time. Okay, same feed to user to some time. Okay, until it is not refreshing in backend. And then I can also use hybrid. Okay, where, so let's say in hybrid I have an e-commerce site. So in e-commerce, if I have a payment related thing, so I will be using their consistency. Okay, and if I have a product catalog thing, so I will be using their what I will be using there. So in product I will be using eventual consistency. Okay, so latency you can say. So yeah, that was about the this database scale.